Hello, everyone. Good day from Ghana. And I first have to thank the organizers of this conference for the opportunity given me to present on our recent research activities on zeolite. I am Bright Kwakye-Awuah. I'm an associate professor in the Department of Physics, KNUST, and also lead the zeolite research group in the same university. I present on catalytic activity of zeolite types LTA and LSX using waste sachet water in a redesigned jacketed reactor. So the rapid depletion of fossil fuel requires that there is the need to explore alternate sources of energy with low environmental impact. This is because common methods of municipal waste disposal, such as incineration and landfilling, have resulted in a global problem. Thermal pyrolysis, which is able to convert plastics into hydrocarbons, can therefore be used as fuels or a source of chemicals. So in going back, we see that these plastics, a heap of plastics somewhere in Europe, and same can be in Africa. And we can see that pollution of plastic goes even way up to the ocean. So over the years, we've been synthesizing zeolite from bauxite and kaolin. And recently we have found that kaolin alone is capable to serve as a raw material for the production of zeolite. This is because the two raw materials in the synthesis of zeolite are aluminum hydroxide, sodium silicate. These two are all being obtained from kaolin only. And so we realize that there will not be the need to use bauxite, but rather we can use kaolin only to synthesize zeolite. But this has resulted in the production or synthesis of other highly important products from the same kaolin. Example is that we have produced aluminum sulfate or alum, and we know this is used in water flocculation or coagulation. And at the same time, it serves as a raw material for high purity alumina. We have produced activated alumina, which is also used in the removal of fluorides. We've produced alumina, the smelter grade alumina, often called the 3N. We have produced high purity alumina, which start from 4N, 5N, 6N grade. And these are used for smartphones, for LED bulbs, for electric car vehicles, and so on. Of course, we have also been able to synthesize silica gel. So all these products we've been able to obtain from kaolin through processes and the use of very few chemicals which are readily available in the market. A bit more into zeolite science and technology, and zeolite are inorganic crystalline solids with small pores, diameter ranging between 1 to 20 angstroms, and that runs through the solid. There are aluminosilicate with framework structures made from corner sharing of either silicon or aluminum tetrahedra. So looking at this structure here, silicon is the central atom here, or aluminum is the central atom. Each of them is bonded at the corners with oxygen and forming the tetrahedron. And this tetrahedron can be arranged or are arranged in such a regular manner such that cavities or pores and formation of cages results. So this is an example of a zeolite which has cages, cavities, and pores. The surface structure of zeolite is negative. Therefore, this negative surface charge is balanced with cations, but the cations are not on the surface, but within the zeolite framework, or what we call the exchangeable site. And these cations are free to move through the zeolite framework, making them accessible for ion exchange. So the ion exchange, normally the cations are soft metal cations, mostly sodium, can be exchanged for other soft metal cations such as magnesium, potassium, or heavy metals such as iron, lead, and so on and so forth. To make the zeolite functionalize as a catalyst, we need to modify the entire framework, the structure, or the internal dynamics of how the zeolite works. The presence of sodium is actually a poison to the zeolite when used as a catalyst. So what needs to be done is to get the zeolite to the barest minimum. So ion exchange is done. Here we do use ammonium ion as the exchanging cation. And we have to say that in addition to the soft metal cations such as zeolite, there are also water molecules. So zeolite can undergo reversible dehydration. So the ammonium ion here is exchanged with sodium ion. The ammonium ion gets into the framework, sodium ion leaves the framework, and this we have to do multiple times in order to ensure maximum ion exchange of ammonium, sodium with ammonium. So once we get the ammonium form, then we can heat at relatively lower temperature, just a little above 200 degrees, and then we can get the ammonia to leave the framework of the zeolite, the ammonium ion. So over here, the reagent used normally the ammonium chloride or the ammonium hydroxide, but when the ammonia leaves the framework and is evolved as a gas, it leaves the H+, creating Bronsted acid site. A further dehydroxylation, that's calcination above 300 degrees, results in the formation of Lewis acid sites within the framework. So these are basic sites that are created within the zeolite to make it functional as catalyst. So what we did was to investigate the catalytic decomposition of waste plastic sachet water using zeolite types LTA and LSX. So this is the original reactor that was bought from China. And then below here is what we did, the modifications that we did. We included the stainless steel reactor for the feed, for the plastics feed, and then also included a vent here, where we will add the catalyst, in this case, LTA or LSX. So we use the LPG gas as a heat source. So we've connected this tube to the gas cylinder here. And then this flux here also, because when heating starts, most at low temperatures, gases are evolved, and these gases are flammable, highly flammable, so they have to be collected far away from the setup to ensure safety. So we varied the temperature between 0 to 400 degrees, because the maximum temperature this borosilicate can take is around 450 degrees. So specifically what we did was to synthesize and characterize the zeolite types LTA and LSX from kaolin only, determine the physical properties of the pyrolysis fuel produced for thermal and catalytic pyrolysis of waste oil. We have to say that we did also work on waste engine oil from vehicles. And so with plastics, we did the pyrolysis with the waste engine oil. It underwent further treatment for refining. We characterize the component of the pyrolysis fuel using various techniques and analyze the thermal stability and decomposition of the waste plastics from dynamic thermoanalytical data and determine the reaction kinetic parameters. So in a summary of the methodology, the kaolin is our basic raw material. It is abundant here in Ghana in trillions of tons. And we synthesize the zeolite from the kaolin, characterized with XRD, SEM, and EDX. And then with the plastic from sachet water, or either plastic from sachet water or used car engine oil, we did pyrolysis with and without zeolite. We obtained the fuel product. We characterized the fuel product with FTIR and GCMS, and then finally determine the kinetic parameters. So basically what we will do is get some 2 kilograms of the plastics or the waste engine oil and vary the heating temperature from 0 to 400 degrees. The holding time, was 30 minutes. And the heating rate was 5 degrees per minute. So every minute, 5 degrees Celsius is added. And we make sure we did that until the temperature reaches 400 degrees. So we're going to show some of the results that we've obtained. And this first is the characterization of the zeolite samples by X-ray diffraction. And what we see here is the zeolite A, which has been characterized about almost 100%, and similar to zeolite LSX. And the peak search matches resulted in, we missed about 3 peaks, which I think will make a lot of, the percentage of zeolite LSX in there is about 90%. Then we confirm what we had from XRD with SCM, and we see the zeolite LTA taking the cubic structure, whilst the LSS take the spherical shapes. And of course, the elemental composition from EDX shows that these two types of zeolite are closely matched in terms of composition. So not much difference in terms of composition. And then we did the characterization also of the engine oil, the virgin, and then the used, the recycled. We determined parameters such as flash point, pour point, kinematic viscosity at 40 and at 100, the viscosity index, the refractive index, and the specific gravity. We did all this to ensure that the zeolite is able to refine the waste engine oil very well. So we did the DSC, differential scanning calorimetry, and TGA also, and we see that the various steps indicate a transformation that is taking place. And so this is for the sachet water, this is for zeolite LTA, very stable, because at the end of it, this is the pyrolysis obtained, the DSC for zeolite LTA, and then this is the uncatalyzed pyrolysis, which has a lot of steps, and each step shows a mechanism, or like I said, a transformation. So the uncatalyzed reaction had 4 distinct decomposition steps within a decomposition temperature of 398.24 degrees. Reaction steps reduced with the application of the catalyst. So for both zeolite LTA and LSX, the reaction steps we can see here, the decomposition steps have reduced significantly, showing that the zeolite really lowered the activation energy. The number of decomposition steps indicates is proportional to the amount, the value of the activation energy. So the reduction of these composition steps by LTA and LSX shows that the activation energy for the pyrolysis in these two processes should be far lower than that of the uncatalyzed. And so we measure the decomposition temperature for the catalyzed. Later on, we shall see. Then we use the Coates-Redfern equation for first order reactions to determine the kinetics parameters, and the Coates-Redfern equation, first order equation, is given as log to the into bracket of log to the 1 minus alpha over T squared equal to all that, where EA is the activation energy, T is the Kelvin temperature, beta is the heating rate, A is the pre-exponential term, and the R is the molar gas constant. So a further modification of this equation, or taking the natural log of this, the Coates-Redfern equation, result in ln into square bracket minus ln of 1 minus alpha, where alpha is a fraction of the feed, either the plastic of the or the waste engine oil that are decomposed at a particular temperature. So a plot of ln into ln 1 minus alpha against 1 over T gives slope with straight line with slope EA over R and intercept of all that. So this plot here is shown. We fitted a linear straight line, a linear fit to the curves. This is to the uncatalyzed, this is for zeolite A, and this is for zeolite LSX. The activation energy, here we obtain 89 for the uncatalyzed. With the addition of zeolite LTA, it is calculated as 25.7486, and then for zeolite LSX is 35.9778 kilojoules per mole. So that's alone here, we can conclude that zeolite LTA is able to lower the activation energy much better compared to zeolite LSX. So we also studied the temperature and catalytic effect on the pyrolysis, and we look at the liquid product distribution at different temperatures, the gaseous product distribution at different temperatures, and then the solid product distribution at different temperatures. So an increase in temperature produced an increase in gas and liquid products, but a decrease in residue. So as the reaction temperature was increased, the gas yield decreased, increasing the amount of oil produced. So over here, in terms of the liquid, we see that the uncatalyzed one is much lower than zeolite LTA and zeolite LSX. So here we can see zeolite LTA is performing much better compared to zeolite LSX, which also performed much better than the uncatalyzed pyrolysis. In terms of the gaseous product distribution, we see that the uncatalyzed one emitted quite a lot, but with the catalyzed with zeolite LTA, much better compared to LSX. And all then solid products we can see here is the zeolite LTA again perform much better, because it's well closely related though, but the zeolite LTA was much better. So catalytic activity showed an increase of liquid yield with a reduction in solid residue. The recovery of condensable fraction was low at low temperatures and increased gradually with temperature. And as we have said, zeolite LTA produced better yield compared to zeolite LSX. And as this is a summary of the kinetic parameters, the activation energy, especially the decompositing temperature for LTA was higher, followed by LSX and the uncatalyzed. The number of steps were 2 for LTA, 3 for LSX, and 4 for the uncatalyzed. We studied the liquid product. The FTIR of the liquid product showed certain peaks, and these peaks are assigned to the various bonds, the ZH bond in alkanes, CH stretch, the ZH single bonds in alkane. So most of the products that were obtained were alkanes, alkenes, and aldehydes, with some 1-amine and some nitro compounds. The GCMS pyrolysis of the liquid products also showed that there were other compounds, such as the cyclohexene, the cyclohexaamine, and the dodecane, the dodecene, the 1-octadecane, 1,13-teradecadene, 1-tridecene, and tridecane. So a mixture of products were obtained during this simple pyrolysis that we did. In fact, we have to say that we are yet to modify the process and even the catalyst so that we are able to fine-tune to a particular product. So these are the methods, the physical properties, the flash point, the density, the rest are all the total sulfur, the cloud point, the pour point are all determined with standards such as those listed here. Like I said, we did some work on the refining of waste engine oil, and we published this work, as we can see here, in Applied Physics Research. We published this work in 2018. And here again, we see that this is a sachet rubber, this LTA, these are FTIR and the TGA of the. We see again here the peaks that are used for the engine oil obtained, the virgin engine oil, the used, and the refined. And we can see that the refined zeolite, the refined engine oil are missing some salient peaks, which are very, very necessary, and or will confirm the steps, the decomposition steps. So the addition of the zeolite improve the purity of the engine oil. So the other parameters here, such as the total acid number, the metallic content, the sulfur content, and the carbon residue, were all determined. And from the list here, we can see that the used engine oil, the recycled engine oil, even perform much better than the virgin oil in terms of the removal of all the metallic content, and then also the sulfur content were much improved after the engine oil was refined. So I have to say thank you to the team, and you have been wonderful people. Working with you had been great joy. And I also have to say thank you to the sponsors. And before I leave, I have to say that, yes, we have the product. We're looking for investors. We're looking for collaborators. We're looking for partnership. We're looking for how we can commercialize some of the products, like the high purity alumina and the aluminum sulfate, so that we can scale it up and go into the market. So all potential investors are welcome, all collaborators are welcome, And I look forward to hearing from anyone who is interested and for us to collaborate and partner. So thank you very much once again. I thank the organizers for giving this opportunity. I'm grateful and look forward for further collaboration between KNUST and UK Catalysis Hub. Thank you very much.